It isn't often that I have a revelation in physics about how to teach something in a new way, but today was one of those days. So a lot of the times you'll come up into problems in physics where they ask you what happens to one thing if you do something to another. So for example, let's say I love to drop things, so let's stay on that. I drop a ball, and it's in the air. I drop it from height h, and it's in the air for a total time of t, just t seconds. It could be 3 seconds or 4 seconds. We'll just call it t. And then I drop another ball. Let's make this one red. I drop another ball from a bigger height, from a higher height, and it takes 2t to hit the ground. How does this second height compare to the first height? So instead of using numbers, like we could use numbers, we could use equations, we could use numbers, but instead of that, we're going to look at this idea of like how the position goes as. And so when I look at this, the position, this line is curved. So if I were to start an equation for this line, it would look something like the position is equal to the time squared. Or I'm going to use this little fish, which means proportional. The alpha is proportional. So position is proportional to time squared. We can find the real equation. We could plug numbers in. We could find this mathematically, but we can also just use the graph to help us out. And so if I said, okay, well, it actually takes 0.3 seconds to fall, that may be around a height of 15 centimeters. And then if I double the time to 0.6 seconds, I now have a height of close to 60. Let's just call it 60 for the sake of things. And so if I doubled the time from 0.3 to 0.6, the height went from 15 centimeters to 60 centimeters. So how did this height increase? Well, 15 to 60 is 4 times. So when I double the time, the height increases by 4, which makes sense here, because if I were to take a number here, and let's just say 3 seconds, right? We'll just make these numbers a little bit rounder. If I said my time was 3 seconds, it would go a position of, about proportional to 3 squared, 9. If I double my time to 6 seconds, I double that, 6 squared is 36. And so 36 is 4 times bigger. So I double the time, the height quadruples. And I'm just going to say 4 times. The height quadruples. If I were to, instead of doubling the time, if I were to make the time 3 times bigger, if I were to triple the time, then the height would increase by 3 squared, or it would be 9 times bigger. If I were to half the time, so instead of it spending more time in the air, I take half the time, well then the height would be a quarter of what it was. If I had half the time, the height would be a quarter. So these two things are related by a squared function. You can get the same thing from a velocity versus time graph, because remember, the velocity versus time graph, the area under this curve is the change in position. And so if I took my time of 0.3 seconds, I could find my change in position here, how far it goes from the beginning. And then I could double my time and see what happens to the area of my triangle. Now, let's just simplify it a little bit. Let's say that this is 100 and this is 200. So let's just say that this is 200 here. We're going to just do a little math. All right. So if this is 100 and this is 200, then the area of my black triangle is 1/2 times the base, 0.3, times the height of 100. And so that gives me 150. And if I were to put units on this, these are using centimeters per second, and this is seconds, so that would give me 150 centimeters is my change in position, or let's call this my height. When I double this, 1/2, I'm going to write it in red, 1/2 base, 0.6 times the height of 200. That gives me an area under this whole triangle, under this whole curve here. 200 divided by 2 is 100. That gives me a value of 600 centimeters. Let me put my units in. And so when I've doubled the time, the height went from 150 to 600. I doubled the time, the height went from 150 to 600, or it's 4 times bigger. So same idea. You can get the same proportionality from the velocity versus time graph. I know that this is getting kind of messy, but before I end the video, I want to think about how does velocity and time, how do they go? And we sort of already figured it out right here. I'm just going to write this in blue. So when I doubled the time from 0.3 to 0.6, when the time doubled from 0.3 to 0.6, the velocity went from 100 here to 200 centimeters per second to 200 centimeters per second. So when I doubled the time, the velocity also doubled. That's the whole thing about this being linear, is that when you do something to one variable, it automatically does it to the other. That's why this looks like velocity is some number, the slope of your line, times time. Whatever you do to the time will happen to the velocity. You double the time, the velocity doubles. You triple the time, the velocity triples. That's what it means to be linear or directly proportional. If velocity goes as time and time squared goes as the height, then we can just substitute the velocity in for here. This is sort of funky. The velocity squared goes as the height.